the interstellar object that broke all of physics, and why NASA is lying. You're about to hear the sentence NASA won't say out loud. The alert chimes cut through the control room. 3/Atlas just nudged off its expected path. No jets, no visible coma, a push with no engine. Someone mutters non-gravitational acceleration, and nobody wants to be the one to say the next part. If it isn't outgassing, what's moving it? A whisper. Oumuamua. Another voice adds sail and gets a glare that says don't start that again. Quick rewind. Third confirmed interstellar visitor flagged by the Atlas survey, labeled a comet, safe, familiar, until the light curve misbehaved and the trajectory wouldn't sit still. The story's already public. The data isn't cooperating, so what is it? Discovery and first label, the comfort of comet. 3 weeks earlier, the Atlas system in Hawaii did what it was built to do, find movers that don't belong. The software flagged a faint point sliding faster than the usual near-Earth rocks, with a trajectory that wouldn't close. Hyperbolic excess speed, past escape. That single number carried a simple meaning. It came from outside the solar system. Interstellar again. Playbook clicked in on instinct. We've seen this before with 2/Borisov, and we wanted it to be that icy, dusty, ordinary in the most comforting way. Initial photometry looked muted but not strange. Magnitude followed distance reasonably. Report writers reach for a label that lands softly with the public, comet. It promises a physical story we understand. Sun warms ice. Ice vents gas. Gas drags dust. Jets tweak the trajectory. If it wiggles, it's alive in a comet way. Behind the scenes, orbital solutions tighten. The path was hyperbolic but clean. Early residuals sat within expected scatter. Observers scheduled follow-ups. The minor planet center queued designations, and agency messaging warmed up. The cadence is familiar. Discovery notice, early orbital elements, cautious language that points to likely cometary. It's like sliding into a well-worn jacket. But from the first nights, there were quirks. Tiny wiggles in the light curve, barely there, easy to shrug off as noise, came back in the next set. The amplitude wasn't huge, but it wasn't the sleepy roll you'd expect from a typical small comet nucleus either. A couple of observers rode each other. Looks like a change in aspect, maybe tumbling, maybe a flattened shape playing tricks with phase angle. Meanwhile, the press notes leaned safe. Interstellar comet candidate. Consistent with a comet. That phrasing does a lot of work. It signals caution without inviting chaos. It tells readers what bucket to put this thing in while leaving a backdoor open if the data refuses to play along. Public appetite rewards certainty. Funding agencies reward prudence. The word comet gives both. In the orbit rooms, nobody complained. The first solutions were tidy, but the photometry crew kept circling those faint brightness undulations. If dust were present, the coma should puff the profile and damp rotational effects. Here, the profile looked point-like in most stacks. The seeing wasn't perfect and the object was faint, so nobody would swear to an absence. Still, the absence was loud enough to notice. Stakeholders lined up like they always do. Survey teams want credit and clarity. The MPC needs taxonomy for its circulars. NASA's outreach needs a line the public understands. Journalists want a headline without a fight. This is the ecosystem. You don't poke it unless you have to. At first, there was no reason to poke. The discovery itself was thrilling, another traveler between stars, yet manageable. The hyperbolic orbit didn't thread close to Earth, so there was no planetary defense angle to complicate things. Observatories passed the baton across longitudes, photometry, astrometry, rinse and repeat. Each night added dots to the arc, and the arc's math smiled back. Then a funny thing about arcs, they get less forgiving as they grow. Tiny mismatches stop looking like random noise and start looking like a signal you've been pretending not to hear. A few analysts added a gentle non-gravitational term to the fit, just to see, and the residuals calmed down. That's normal for an active comet, except if you're going to claim cometary thrust, you want evidence of the engine, jets, dust. A whisper of gas lines in spectra. Anything. In public, the language didn't change. Likely a comet. The comfort of that word holds the room together. It reassures people who remember the Oumuamua brawl and don't want to relive it. But in late-night emails, a new phrase showed up: non-gravitational acceleration. Not big, not alarming, just persistent. One tiny loop refused to close. If it's a comet, where's the coma that should make it obvious? If it's not a comet, why is it moving like one that's venting, and what's doing the pushing? You can carry both thoughts for a while. You can say the data are early, the object is faint, the stacks are shallow. That buys time. It doesn't buy answers. While the press releases settled on comet, the data team started watching the light curve like a heartbeat monitor. It wasn't flat. It wasn't chaotic either. It hinted at shape, at spin, at geometry that matters. And if the geometry matters, the label might not. Which is where this story stops being comfortable and starts getting real. The light curve problem, tumbling or paneling. To see what the brightness was saying, you start with the basics. As a small body spins, the surface area facing us changes. More area, more reflected light, brighter frame. Less area, dimmer frame. Simple, until the amplitude gets too big for a normal lumpy pebble of ice and dust. That's what crept out of the first clean runs. The peaks were sharper than they should have been, and the troughs fell deeper. The curve looked less like a gentle wobble and more like a slow blink. Now here's the catch. The object didn't show the soft halo you'd expect from even a modest coma. In comets, dust acts like a lampshade, smoothing out brightness swings. If the lampshade isn't there, we're seeing the bare reflector. And the reflector, based on the amplitude, didn't behave like a squat sphere with scars. It hinted at either an extreme aspect ratio, long and thin, or wide and flat, or surface patches capable of catching sunlight like a mirror. Specular flashes don't need a lot of area, they need alignment. That pulled the conversation right back into familiar trouble. With Oumuamua, teams argued cigar versus pancake because the light curve could fit both depending on your assumptions about albedo and phase angle. The same degeneracy hovered here. If the albedo is low, cold dark, you infer a larger body. If the albedo is higher, it can be smaller. But the amplitude doesn't care about size. It cares about shape and orientation. The bigger swings mean the silhouette is changing a lot as it turns. Period analysis didn't bail us out. A single simple spin period couldn't explain the subtle sidebands that kept showing up. That often points to tumbling, a non-principal axis rotation, where the object isn't spinning cleanly around one axis but wobbling. Tumbling is common in small bodies after close passes or torquing events. Comets can tumble too. The problem was the stability. Over multiple nights, the pattern stayed coherent. Jets should nudge the rotation state. Without visible jets, what's adding the torque? Or is the torque coming from sunlight? This is where the geometry starts whispering about panels. Imagine a flat sheet with a slight tilt. As it turns, the projected area toward us can jump from almost nothing to a broad face, producing strong brightness swings. If parts of the surface are smooth, you might get glints, brief peaks sharper than a rough rock would allow. A plate-like geometry also couples strongly to radiation pressure and radiation torque. Sunlight doesn't just push, it twists. Observers chase the phase angle dependence. As the object's angle to the sun, observer line changed, the curve's contrast shifted in a way that didn't quite match standard cometary phase functions. There was an opposition surge, an extra brightening at small phase angles that hinted at surface microtexture effects. That alone doesn't prove a thin sheet. But it fits more naturally if the surface has large-scale flatness overlaid with sub-millimeter roughness. Think a thin film with frost or dust welded on. With dust absent in deep stacks, albedo assumptions became the wild card. If you pick a comet-dark surface, you get a larger, thicker body that's hard to push. If you assume a brighter, smoother surface, you can keep mass down while keeping the same optical signature. That's why the light curve tied into the propulsion question. A thin, broad object can be small and feather-light yet bright enough to see. The area-to-mass ratio jumps, and suddenly sunlight doesn't need to work hard to matter. But there was another tension. If you invoke outgassing to explain non-gravitational acceleration, You should also expect flicker from jets crossing the limb, little asymmetries that evolve as vents turn on and off. Instead, the brightness pattern felt more clock-like than weather-like. That steadiness suggested the source of torque wasn't sporadic eruptions, but a persistent effect linked to orientation relative to the sun. Radiation torque, YORP-like effects can do that, especially on shapes with broad, flat facets. Back to tumbling. If it's tumbling, the energy has to go somewhere. Outgassing usually damps or excites certain modes. Sunlight can also nudge modes, but very gently. The observed persistence implied low dissipation and minimal impulsive forcing. That favors a rigid structure with a high quality factor rather than a loose rubble pile. Porous fluff can produce big photometric swings too, yet it tends to behave like a thermal sponge, lagging and smearing signals. Here, the curve's edges were too crisp. So the stakes sharpened. Get the shape wrong, and every downstream inference collapses. Thermal modeling depends on thickness. Mass estimates depend on albedo. The viability of radiation pressure as a driver depends on the area-to-mass ratio. Even the viability of natural versus artificial possibilities leans on geometry. A brick can't fake a sail's light curve. A sail can fake a brick's average brightness, but not its tight, symmetric wobble. What nobody could ignore was the alignment between three facts: large amplitude without a coma, coherent modulation over weeks, and non-gravitational acceleration in the orbit fits. Separately, each can be waved off. Together, they pointed to a thin, broad surface that both reflects and feels sunlight. It didn't prove anything beyond doubt. It did put shape on the same side as the trajectory anomaly. And once shape sits there, every conversation about what's pushing starts sounding less like engine noise and more like sunlight. Trajectory anomalies, non-gravitational acceleration without a tail. The orbit fit was supposed to be the boring part. You feed in astrometry, let gravity do its work, and the residuals shrink. But as the arc lengthened, the dots wouldn't sit on the gravity-only curve. The analysts added a standard non-gravitational term, the A1 radial component that in comets stands in for jet thrust pointing roughly away from the sun. The scatter calmed. The math breathed a little easier, but there was a catch. This object wasn't wearing a coma. Teams pushed the imaging deeper. Stacks that should have teased out a faint dust halo stayed quiet. No robust tail. No broadened point spread function beyond what seeing and motion smearing explained. If jets were pushing, they were doing it with remarkable stealth. Deep limits on dust production meant any venting had to be exquisitely fine, gas-rich and dust-poor, and still somehow strong enough to nudge a kilometers per second traveler. That contradiction sat at the center of the room. In the standard comet model, sublimating volatiles expand, drag dust, and the asymmetric mass loss imparts thrust. You see it in the sky as a fuzzy head and a tail. Here, the thrust signature was in the orbit, not in the images. You could try to save the model by invoking hypervolatile ices, CO or CO2, sublimating at larger heliocentric distance, producing mostly gas. But then you'd expect a thermal story, heating, line emission in the infrared, or at least subtle color changes. Infrared constraints came in tight. The expected warmth didn't show. So the alternative crept into the spreadsheets: solar radiation pressure. Sunlight carries momentum. For most rocks, the effect is tiny, gravity dwarfs it, but give sunlight a large cross-section and very little mass, and that gentle push matters. Back-solve the measured acceleration and you land on a high area-to-mass ratio. That's sail territory. It doesn't prove a sail. It just says the shape and mass would need to cooperate like one. The skeptics asked the right questions. Could porous fluff, an ultralight aggregate, mimic a sail's response? Possibly. But then you have to carry it through interstellar space without it being shredded by collisions or compacted by micro-impacts. You also need it to survive perihelion heating without slumping, and to maintain a rotation state that keeps the acceleration direction stable enough to match the A1-like fit. Each fix added a new burden on the material strength and thermal history. Meanwhile, observers kept cross-checking the non-grav term against geometry. If you assume radiation pressure, the the acceleration vector should correlate with the sun-object line and with the object's attitude. The residuals liked that story. An A1 dominant solution, with tiny tangential or normal components, did better than a pure gravity fit and didn't need time variable thrust spikes. It looked less like episodic jets and more like a steady, sun-locked push. The absence of gas detections became its own data point. Spectra that easily flagged activity in Borisov stayed quiet here. No cyanogen bands shouting. No water proxies lighting up. At the same time, thermal models that would predict a warm skin under active venting ran into the infrared non-detections. If venting was real, it had to hide both its dust and its heat. That's a narrow alley. At this point, the room split not into aliens and not aliens, but into two flavors of discomfort. One side said, the physics is fine, the object is just weird. Maybe a dust-poor, volatile-rich shard with vents so small they leave no signature. The other side said, the object can be ordinary if you let sunlight be the engine, but ordinary then means extraordinarily thin and light. Both options demanded a step away from the middle. Here, where the light curve and the orbit shook hands. The coherent modulation over weeks suggested a stable geometry. The non-grav acceleration suggested a stable push. If radiation pressure was doing the pushing, the same broad surfaces creating brightness swings would naturally couple to that force. You don't need to tune vent locations or invoke thermal lags to keep the acceleration direction steady. The sun points, the sheet feels it, the orbit records it. There were sanity checks. Could small catalog biases or astrometric systematics mimic a non-grav term? With a short arc, you always worry. Analysts reweighted stations, trimmed outliers, tested alternative ephemerides. The signal persisted across datasets. Whether gaps didn't create a fake trend, they just widened the error bars. As time passed, the confidence on something extra is pushing climbed, even as the error on what exactly is doing it refused to shrink. And then there's the directionality test. Jet thrust often wanders as vents open and close, or as spin carries active areas in and out of sunlight. You see curvature in residuals that changes character over weeks. Here, the required acceleration felt smooth, almost boring in its steadiness. That's friendly to radiation pressure and unfriendly to spiky vent models without visible support. None of this forced a verdict. It forced a choice of discomforts. Accept a comet that doesn't look or heat like one, or accept a high area to mass geometry that lets sunlight do real work. Official language tiptoed, consistent with a comet. Inside the spreadsheets, the numbers kept pointing at a thin, light body that sails more than it sputters. And in that quiet consistency, the orbit started telling the same story the light curve had been hinting at all along. The comet that wouldn't behave failed natural explanations. Before anyone reached for sails, the room did what scientists always do, try to save the simplest story. If a comet's jets can push, then weak jets might push quietly. So teams ran the numbers for CO and CO2 outgassing, volatiles that can sublimate far from the sun and carry little dust. The acceleration we measured demanded a gas production rate that should have left some fingerprint, broadened profiles, faint emission features, or warmth in the infrared. Deep stacks didn't show a coma. Spectra didn't show lines. Thermal limits stayed stubbornly low. You can hide small vents, you can't hide all the consequences at once. Next came exotic ices. Maybe it was CO or CO2. Maybe it was something rarer, like N2 or even H2 trapped in amorphous lattices, breaking free as the object warmed. The thermodynamics didn't line up. At the distances involved, the latent heats and sublimation curves either gave you thrust too weak to matter or activity that should spike and fade with temperature swings. The orbit's non-gravitational term looked smooth. The light curve's modulation looked steady. Episodic venting didn't fit that calm. The fluffy aggregate idea tried to thread the needle. Imagine a fractal snowflake of dust, extremely porous, barely held together, so light that radiation pressure bites hard without needing a sail. On paper, that boosts area to mass without changing brightness too much. But then you ask how an ultralight aggregate survives interstellar travel. Millions of years of micro-impacts and sputtering compact fluffy structures. Solar heating near perihelion can sinter them or make them slump. If it compacts, the area-to-mass ratio falls, killing the very mechanism that made it useful. If it doesn't compact, you expect thermal lag and delayed outgassing signatures as heat soaks through a sponge. Our brightness swings were crisp, and the thermal searches were quiet. Spinjet coupling was another rescue attempt. Put a few vents in the right places, let the nucleus spin, and you can create a quasi-steady thrust that mimics a constant A1 term. That trick works for active comets when you can see jets and tails. Here, you had to tune vent strength, placement, and thermal response to keep the push aligned while somehow producing no visible dust and minimal heat. Worse, the rotational period stayed coherent. Active jets usually torque the spin state measurably over weeks. We didn't see evolving sidebands consistent with fresh torque. A model that needs jets but punishes you when they actually torque is balancing on the edge of special pleating. Dust constraints tighten the vice. If grains were large, they could be invisible in certain bands yet still carry momentum. But large grains decouple from gas and won't follow smooth, sun-locked patterns. They'd shed asymmetrically and leave trails. If grains were tiny enough to be dragged cleanly, they would brighten the coma. Deep stacks capped dust production so low that any gas strong enough to drive the orbit would have to be dust poor in a way that's rare and across weeks, improbably consistent. Thermal lag thrust models tried one more angle. Heat the day side, vent from the afternoon limb, get a gentle, phase-locked push with minimal dust. The physics of cooling timescales fought back. To keep thrust smooth, you need a thermal skin depth and conductivity that produce a delayed but steady response. Those same properties should show up as color changes and infrared warmth detectable with sensitive instruments. The IR non-detections undercut that balance. If you tune the thermal inertia low to hide IR, the thrust gets spiky and wrong way. Tune it high to smooth thrust and you glow. People revisited composition with laboratory analogs. Could CO-rich pockets in a refractory mantle percolate gas through micropores, adding thrust without dust? It's possible in principle, but permeability models predict evolving channels, surges, and collapses as pathways open and clog. That creates noise in both the light curve and the orbit residuals. Our data preferred boring steadiness. Every new natural mechanism that produced a steady push required laboratory perfect homogeneity in a body that likely formed in chaos. Then there's survivability. Exotic ices like N2 and H2 don't love long-term space exposure. They sublimate away on million-year timescales unless buried deep. If buried, they can't vent steadily without heating that should betray them. If shallow, they vanish before the object arrives. Even if you grant a protective crust, once activity starts, the crust should pit and spall, leaving dust signatures we didn't see. A few proposals got creative. Maybe electrostatic lofting of fine grains mimicked a jet without producing a coma. Maybe sputtering by solar wind removed atoms gently. Electrostatic lofting needs local fields and day-night cycling that should imprint diurnal changes. Sputtering rates are too low to produce measurable acceleration at these distances. Each clever idea clipped against hard limits, photon counts, heat budgets, or simple momentum math. By the end of this triage, the ledger looked lopsided, and the brain hates lopsided stories without closure. That discomfort is a feature we can use to ask for the decisive measurements. On one side, radiation pressure needed a high area-to-mass geometry that also explained the light curve's amplitude and stability. On the other, natural outgassing needed low dust, invisible heat, fine-tuned vents, exotic ices that survive the trip, and rotation that doesn't drift. None of those alone is impossible. Together, they ask for a miracle of coincidences that repeats for weeks. This didn't crown an artificial origin. It did corner the ordinary comet claim. To keep that label, you had to bend every parameter toward the edge of plausibility while ignoring the clean fit between a thin, broad surface and a steady sun-locked push. That's why, even among conservative voices, The phrase weird natural object replaced just a comet. And once you admit weird, the door to engineered geometry isn't open wide, but it's no longer locked. Oumuamua's shadow, lessons and biases. 3 letters haunted every late-night thread. One eye Oumuamua left a mark that wasn't just scientific, it was social. Back in 2017, the first interstellar visitor arrived with the same awkward pairing, non-gravitational acceleration and no obvious coma. Everyone remembered the social blowback, the spotlight effect, the reputational risk, the way a single spicy frame hijacks attention and punishes nuance. The fight that followed split colleagues into camps, hardened language, and taught institutions a survival tactic. If the data get weird, talk softly and keep to natural explanations until the storm passes. You could feel that reflex kick in with 3-Eye Atlas. People who'd spent years repairing the Oumuamua fallout weren't eager to relive headlines about alien sails. That episode turned careful speculation into caricature. A few researchers argued for radiation pressure, others floated exotic ice. The press jumped to alien probe. Careers got reduced to a meme. The scars didn't fade. So when 3-Eye started humming a familiar tune, steady brightness modulation, gravity dodging orbit, there was a visible flinch. Inside labs, the lesson of Oumuamua was simple: ambiguity gets weaponized. If you don't control the frame, someone else will. The defensive move was to front-load priors. Comets are common, engineered objects are. Therefore, say comet, add consistent with, and bury caveats in the methods. It's not deception, it's harm reduction. But it carries a cost. Language that protects credibility can also blunt curiosity. When your first word shapes the next grant panel's mood, you choose it carefully. There's also the peer review memory. Papers that dared suggest radiation pressure for Oumuamua walked a gauntlet. Reviewers demanded tighter bounds, more exhaustive alternatives, stronger priors for natural origin. Good practice, sure, but the asymmetry grew obvious. Extraordinary claims needed extraordinary evidence. Ordinary claims only needed consistency. The problem is that ordinary became a moving target. For Oumuamua, ordinary stretched to nitrogen icebergs, hydrogen flakes, and fractal fluff that almost nobody could manufacture in a lab. Each patch saved the label while straining the physics. Outreach teams learned their own lesson. In the media space, nuance underperforms. Say we don't know yet and the clip dies. Hint at aliens and it lives forever. After Oumuamua, agencies adjusted, pre-brief reporters with conservative lines, avoid speculative verbs, emphasize natural analogs. That approach kept the temperature down. It also made the public think the science was settled when it was. By the time deeper analyses landed, memory had fossilized around the earliest phrasing. Meanwhile, on the telescope floor, the bias didn't look like dogma, it looked like triage. Nights are scarce. You can chase an interstellar oddball or stick with proposals that promise guaranteed results. If your last foray into weird object turned into months of sideways attention, you remember. Committees remember too. A file stamped alien tech hypothesis can be a career magnet or a career sink, depending on who's reading. This is where 3-Eye's data started rubbing that scar tissue raw. The same pattern non-grav push without a tail should have triggered an open question. Instead, the institutional muscle memory reached for the softer landing. Likely comet, consistent with cometary activity. The careful qualifiers did their job, but in newsroom retellings, consistent with slid into is. Then the next press cycle quoted the last one, the frame locked. Frontline researchers didn't all agree. Some leaned into the exotic natural space with better models. Others argued for leaving the artificial geometry hypothesis on the table with testable predictions. Specular flare searches, polarimetry for thin films, tighter IR. But the atmosphere shaped how bold you could be in public. After Oumuamua, nobody wanted their name fused to aliens by an editor's cut. So debates moved to private Slack channels and hallway conversations, while public statements stayed cautious. There's another bias Oumuamua left behind, the temptation to solve everything with one special object. If the first interstellar visitor forced contortions, surely the third could be a normal comet and restore order. That hope nudged interpretation. When you want equilibrium back, you welcome every dust-poor jet model that buys it. The danger is that desire can tilt which uncertainties get emphasized. With 3I, uncertainties around albedo and mass became shields for comfortable conclusions, while uncertainties around thermal non-detections and torque steadiness got framed as pending improvements. None of this implies bad faith. It's the sociology of high stakes, low signal science. We learned to speak softly after Oumuamua because the blowback was loud. We learned to prefer natural until proven otherwise, because that stance is safer in grant narratives and press kits. But safety isn't the same as truth-seeking. The lesson that should have stuck was different. Say what the data say and stop there. With 3I Atlas, the honest line was simple and uncomfortable. There's a persistent, sun-locked acceleration without the usual signs of outgassing, and a light curve that favors a thin, broad geometry. Everything beyond that is a hypothesis. The fear of repeating 2017 turned that sentence into softer ones, and in that softening, the next hard question slipped a little further away. Spectral silence, what the colors didn't say. While dynamics and brightness hinted at something thin and broad, the spectrographs were supposed to close the case. If it's venting, you expect chemical fingerprints. If it's inert, you expect a quiet, featureless continuum with colors shaped by space weathering. What we got was somewhere between neutral to slightly red broadband colors, the kind you see on weathered outer solar system surfaces, and a spectrum that refused to shout active comet. Observers went hunting for the usual suspects. Cyanogen bands, water proxies, CO or CO2 lines, anything that would betray gas in the coma. The signal to noise was honest but limited. You can't conjure photons from a faint target that's hustling out of reach. Still, even within those limits, activity like Borisov's would have lit up. It didn't. Compared side by side, 2I/Borisov was noisy with life, gas, and dust flying. 3I Atlas stayed quiet enough that absence itself became a clue. The colors told a restrained story. Slight reddening tracks with micrometeoroid gardening and radiation darkening, a common fate for airless bodies. That by itself doesn't separate rock from ice, nor natural from engineered. But it argues against a fresh, icy coma brightening the near UV and blue bands. If vents were spraying, subtle slopes and narrow emissions tend to ride on top of the continuum. Analysts stacked exposures, subtracted sky, and pushed calibrations hard. The lines weren't hiding, they just weren't there. Phase behavior added another wrinkle. At small phase angles, the object showed an opposition surge, an extra brightening as shadows close up and coherent backscatter kicks in. Classic for rough regolith, except the magnitude and shape of the surge leaned unusual, like a surface that's overall smooth at macro scales but carries micro roughness that enhances backscatter. Think thin film with a frosty skin, not a fluffy dust ball with deep pores. It's a hint, not a verdict, but it rhymes with the light curve's call for broad, flat facets. Skeptics pointed to SN. Maybe the lines are there just buried. Fair push. But even buried lines have consequences. Gas production strong enough to drive the measured non-gravitational acceleration wants to heat the skin and alter color slopes in predictable ways. Thermal non-detection squeezed those models. So the spectrum's quietness teamed up with the IR silence to say, if gas is present, it's shy, steady, dust poor, and uncharacteristically invisible across bands we're good at reading. Polarimetry would have helped. Linear polarization angles can reveal surface roughness and thin film interference signatures. Time and geometry weren't kind. The windows were narrow, weather stole nights and priorities leaned toward astrometry to keep the orbit pinned. So the spectral record stands as a careful shrug, consistent with a space-weathered, relatively inert surface, inconsistent with a lively comet flaunting its chemistry. Here's the subtlety that mattered in the room. Consistent with isn't a label, it's a corridor. Neutral to slightly red colors and a quiet spectrum keep you in that corridor for asteroids, dormant comets, and engineered materials that have spent time getting sandblasted by interstellar dust. The absence of strong emissions doesn't prove intelligence any more than a tail proves ice. It just removes the easy exit, a comet loudly advertising its vents. Meanwhile, the continuum shape and color ratios fed back into size and albedo estimates. If the surface is darker, you scale the object bigger to match its brightness, harder to push, worse for radiation pressure. If it's brighter, you can shrink it, lighter, friendlier to sunlight. With no coma to dilute the light curve, the spectral slope quietly nudged the models toward higher albedo patches or smoother surfaces, both of which play well with specular reflections and radiation torque. The numbers didn't lock, but they leaned. A few teams checked for time-variable color changes, flare-ups that might mark episodic venting. Night to night, the colors hugged their error bars. No obvious bluing events. No reddening surges as fresh dust lifted. That steadiness matched the clock-like modulation in brightness and the smooth non-grav term in the orbit fits. The spectrum wasn't just quiet, it was consistently quiet. Compared to Borisov's textbook comet signature, 3I Atlas read like a closed book. That silence didn't kill the comet idea, but it starved it. To keep calling it an active comet, you had to argue for gas so clean it writes no lines, dust so scarce it leaves no veil, and heating so modest it leaves no thermal footprint, all while producing a steady push. The spectral data didn't endorse that contortion. They just didn't rescue it. So the chemistry didn't decide the argument. It narrowed it. With no loud emissions to pin composition, the spectrum handed the microphone back to geometry and dynamics. Neutral colors, quiet lines, and unusual phase curve. Together they supported a surface that reflects well, holds structure, and couples efficiently to sunlight. When the photons won't tell you what the stuff is, they can still tell you how the stuff behaves. And behavior here kept pointing in the same direction as everything else. Radiation pressure math, when sunlight does the pushing. Start with the number that wouldn't go away. The extra acceleration fell roughly where sunlight lives, small, steady, pointing away from the sun. Backsolve that value and it hands you an area-to-mass ratio that's too high for a compact rock. You don't need exotic algebra. Momentum from photons is tiny, but it's relentless. Give those photons a big sail and very little mass to carry, and they move the needle enough for orbit fits to notice. So what does the math actually ask for? A sheet-like object with dimensions large compared to its thickness, surface reflectivity decent enough to double-count momentum on bounce, and a mass per unit area in the ballpark of grams per square meter. That's sail country. Human-built solar sails flirt with similar aerial densities, tens to single-digit grams per square meter in lab prototypes. If you knock reflectivity down to match a weathered surface, you can still land near the needed push if the sheet stays thin and broad. Natural options try to sneak in. The fractal fluff idea says build a low-density lattice, huge cross-section, tiny mass. But interstellar space isn't gentle. Micro-impacts erode delicate structures. Gas drag across star-forming regions compacts them. Occasional shocks rearrange bonds. Even if a fluff survives, near-sun heating should stiffen or collapse pores, changing the area-to-mass ratio at precisely the moment our data say the acceleration stayed smooth. The sail math wants stability. Fluff physics invites evolution. Thermal constraints line up awkwardly for jets, but neatly for a thin radiator. A sheet with large area bleeds heat effectively on both sides. Its equilibrium temperature can sit lower than a chunky body, S at the same distance, especially if it reflects well. Those cooler skins help explain why infrared searches stayed quiet. There's no hidden furnace driving gas. There's a big radiator sipping photons and shedding heat across space. Now fold in the spin. Radiation pressure isn't just a shove. Off-center forces and anisotropic reflection create torques, the YORP-like family of effects. A broad, flat shape naturally couples to these. Under steady sunlight, it can settle into a stable attitude where slight tilts produce restoring torques, like a weather vane in a slow wind. That stability shows up in the light curve's coherence and the orbit's calm non-grav turn. You don't need to fine-tune vents, you let geometry do the work. Skeptics asked about reflectivity. Comet dark surfaces won't catch photons like a mirror. True, but even a modest albedo surface gets pushed. Absorption transfers momentum too. Reflectivity boosts the push, not creates it. If the spectrum hints at a weathered, slightly red surface, you assume middling albedo and adjust thickness. The areal density target stays reachable if the thickness is sub-millimeter and the bulk density low. Metals would be heavy, composites or foams go lighter. Nature could in theory make foamy silicates, but again, survivability across light years and perihelion passes is the wall you hit. Another check, directionality. If radiation pressure rules, the acceleration aligns closely with the sun object line, modulated by attitude. The fits preferred a radial term, A1 dominates, while tangential tweaks stayed small. That's the signature a sail-like body gives when it isn't aggressively steering. It's also the hardest behavior for thermal lag models to clone without betraying themselves in infrared. The photon ledger balances, the heat ledger doesn't. People tested the sensitivity. Lower the albedo, thicken the sheet. The required push climbs, and at some point the material budget breaks. Raise the albedo, thinner sheet, friendlier numbers, stronger specular glints, exactly the kind of flicker the light curve teased. The math doesn't demand a mirror. It rewards surfaces with coherent patches. Even partial specularity can spike brightness without wrecking the average color. What about rotation state drift under radiation torque? Over weeks, you'd expect slow evolution. We did see hints of minor sideband changes, consistent with gentle torques nudging a high-Q structure. No violent jitters, no jet-driven spin-up. The timescale matched YORP-like expectations at this size and distance, especially if the moment of inertia is dominated by a plate rather than a lump. Again, the geometry that makes the shove work also makes the twist plausible. There's a population question embedded in the math. If 3I Atlas is natural, how many thin, broad, ultralight rafts must be launched by collisions or tidal tearing to make one wander into our surveys? Production rates have to be huge, and the survival fraction small. Radiation pressure math doesn't answer population, but it exposes the cost. Every natural pathway must mint sails by the billion, and most will die before we meet them. If it's artificial, population is a different equation, deployment strategies rather than accidents, but the physics is the same. The sunlight doesn't care who built the geometry. A final sanity pass looked at phase curves under a sail assumption. A broad plate with micro-roughness produces opposition surge behavior within the observed range, especially if the surface is layered, thin film over granular patches. It's a comfortable fit next to the awkward acrobatics required by dust-poor, heat-poor jets. Different priors, same photons. The consistent story wins. So the ledger on sunlight reads clean. The acceleration scale matches a high area-to-mass body. The direction aligns with the sun. The thermal quiet helps, not hurts. The spin behavior fits radiation torque more naturally than jet torques. And the light curve's sharp amplitude looks like facets doing exactly what facets do when the star is a relentless wind. You don't need to declare intention to accept that geometry. You only need to accept the push. The data we didn't get, observational gaps and uncertainties. Before we crown a culprit, we have to face the holes in the record. The observation arc was short, weeks that felt like days. With interstellar visitors, geometry is cruel. They brighten too late, fade too fast, and race out of range while committees are still approving time. Small astrometric errors that wouldn't matter over months can masquerade as real forces when you only have a sliver of orbit. Analysts know this. They stress-test fits, reweight stations, and still, the clock wins. Weather did its part. A run of bad seeing here, a lost night there, and the cadence breaks. That matters for light curves. Miss a few cycles, and you alias periods, invent harmonics, or smooth over specular flares you should have caught. It matters for orbit fits too. Gaps amplify parameter covariances. letting a tiny bias in one-night pull on the non-gravitational term. We pushed cross-calibration as hard as we could, but different instruments with different filters and motion smear corrections don't line up perfectly. Every handoff adds millimag and milliarcsecond noise that stacks into doubt. Selection affects loom over everything. Our surveys preferentially net the oddballs, the bright, the high area to mass, the dust-rich. The bland interstellar pebbles slide under detection limits, unfelt and uncounted. That biases our priors. If sails or sail-like geometries are overrepresented because they're easier to see and push, we'll keep discovering thin, bright objects and thinking the universe is full of them. Or flip it. If only active comets scream loud enough for early detection, then quiet, inert slabs sneak by and get labeled exotic when we do catch one. Either way, our sample is skewed, and our models inherit that skew. Model degeneracy sits in the center of the table like a polite dare. The same sparse data let multiple parameter sets fit acceptably. A dust-poor jet model with tuned vents, a radiation pressure model with a high area-to-mass ratio, a porous aggregate model that toes the survivability edge. With incomplete phase coverage, you can trade albedo for size, thickness for reflectivity, and walk away with very different bodies that all match the points. Consistent with becomes a chorus because unique solution never shows up. We also lack decisive polarimetry. Polarization angles can betray surface roughness in thin films, but windows were tight and priorities leaned to orbit tightening. Thermal infrared coverage was better than nothing, worse than ideal. Sensitivity floors that rule out big heat don't entirely kill small, steady warmth. A deeper IR campaign earlier, days, not weeks, might have cornered thermal inertia and buried some jet models for good. We didn't have it. By the time proposals moved, the target was dimming into the noise. Even the spectrograph suffered from geometry. High air mass passes, moonlit skies, and rapid non-sidereal tracking degrade line sensitivity. A cyanogen band that would pop against a dark sky sinks into residuals when scattered light rises. We corrected. We subtracted. We still lived in the tail of SN. It's honest to say lines weren't seen. It's also honest to say deeper, cleaner nights could have lowered those limits further. Astrometric systematics were another worry. Different observatories use different star catalogs and plate-solving pipelines. Small zonal errors can nudge centroids in a way that looks like a gentle push. Teams tried to homogenize reductions, reprocessing frames against the same reference and trimming outliers aggressively. The non-grav term persisted, but the error bars breathed with every cull. That's how it goes when your quarry fades faster than you can standardize your tools. There's a human bias baked in, too. Once non-gravitational appears in a circular, follow-up time gets easier to secure for people asking questions that assume it's real. That improves orbit coverage, good, but it also channels the kinds of measurements you get, less good. Nights that might have chased polarization or time-resolved color went to astrometry and broadband light curves. Sensible triage, but it left certain discriminants underexposed. So what does uncertainty actually do here? It cuts both ways. It weakens a confident active comet because the key signatures dust, heat, lines sit under limits. It also weakens a confident sail because aerial density and reflectivity live inside degeneracies you can't break without better phase coverage and polarimetry. The gaps don't absolve one model, they discipline both. They say, be precise about what the data force and what they merely allow. And yet even inside those holes a pattern held. A sun-locked, steady acceleration, a light curve that favored broad facets, spectra that stayed quiet, IR that stayed cool. Uncertainty didn't erase the alignment. It just kept us honest about the word we couldn't say yet, confirmed. The narrative lock, why institutions hug the comet. While the spreadsheets pointed to a thin, light geometry, the public story did something else. It settled. Not on certainty, on safety. Inside agencies, risk management isn't a slogan, it's muscle memory. After years of fending off bad faith headlines, the guidance is simple. Avoid fueling fringe narratives. Protect mission credibility. Don't hand a clip to someone who will turn non-gravitational into alien engine before lunch. That's how likely comet becomes the first line you see and the last one anyone remembers. And that's the psychological trap. A safe label dampens curiosity, kills the follow-up questions, and locks the narrative before the best data arrive. Press kits did their quiet work. Drafts circulated with the same phrasing, consistent with cometary behavior, no evidence of artificial origin, interstellar comet candidate. The caveats lived there, words like consistent with, candidate, no evidence of, but they stacked behind the noun that frames the mind, comet. The result is tidy. It heads off speculative questions, reinforces familiar mental models, and keeps phones from exploding with requests for quotes about sales. It also cages the science in language that the data hadn't fully earned. Internally, the emails sounded different. Memos flagged the non-gravitational term, the lack of a coma, the quiet spectrum, the IR limits. They asked for deeper stacks, polarimetry if possible, more nights for astrometry to rule out catalog systematics. Careful, measured, accurate. Then somewhere between draft and tweet, the tone shifted. The public posts trimmed the hedges and kept the label. It wasn't deception, it was triage under time pressure. But that split, cautious inside, confident outside, became the narrative lock. Historical precedent played referee. Outliers get downplayed until peer review coalesces. That norm protects journals from becoming battlegrounds for every shiny anomaly. It also delays honest uncertainty in front of the public. The first impression anchors. By the time a nuanced preprint lands, headlines have fossilized and corrections underperform. The next article quotes the last, and consistent with quietly morphs into is. Funding realities press from the sides. Missions ride on public trust and congressional patience. If comms teams let sail, float unchallenged, hearings get awkward. Outreach staff know how that story goes. So institutional messaging leans conservative. Emphasize natural pathways, point to known comets, draw parallels to Borisov where possible, and bury the unresolved bits in technical pages almost nobody reads. It's not a conspiracy. It's incentives doing what incentives do, and incentives shape attention. Attention shapes memory. Memory shapes budgets. Scientists inside the machine felt the squeeze. A few pushed for neutral labels, Interstellar Object with non-gravitational acceleration, arguing that clarity keeps options open. Outreach pushed back, neutral reads murky and murky bleeds attention. The compromise was that middle phrase, consistent with a comet, which satisfies lawyers of language while calming editors. Except consistent with is a logic trap when data are sparse. Many models are consistent, none are confirmed. Here's the cost you don't see on a press release. Language shapes telescope time. Proposal panels scan abstracts fast. Active comet suggests a proven playbook. Coma physics, dust modeling, gas lines. Non-gravitational acceleration of unknown origin suggests risk. When nights are scarce, risk loses. The narrative, set early, reaches forward and trims the very observations that could have broken the tie. Polarimetry, rapid response IR, coordinated specular flare campaigns. The label picks the measurements justify the label. Loop closed. Media dynamics add the final lock. Editors want verbs. Is a comet reads clean. Consistent with a comet pending further observations that may or may not arrive in time does not. So reporters flat, not maliciously, efficiently. They're racing deadlines, they mirror official phrasing, they compress nuance. The next wave of coverage quotes the first, and institutional accounts amplify the echo because it's accurate enough and safely framed. By the end of week 2, the public thinks the case is solved. Against that tide, a few researchers tried threading the needle, talk about priors and likelihoods, remind audiences that natural doesn't mean normal, explain that the same numbers pointing to a sale like geometry don't imply intention. Some long-form pieces carried that nuance, most didn't. And in the background, careers weighed in. Nobody wanted to be the alien person twice. Grants remember names, committees remember frames. So why hug the comet? Because institutions are designed to minimize reputational risk in environments where attention punishes ambiguity. Because early language echoes longer than late data. Because Comet keeps the phones quiet and the budgets boring. None of that makes the official line dishonest. It makes it incomplete. The honest public sentence was short and uncomfortable. A sun-locked, steady acceleration without visible outgassing. A light curve that favors broad facets, spectra and IR that stay quiet. Instead, we got consistent with a comet. That phrase soothed the moment and shifted the burden. It asked skeptics to prove a negative while letting confidence ride on consistency alone. The irony is that caution about speculation can become speculation by omission. When the safest label outruns the evidence, the narrative locks before the science does. And once it locks, the next observation has to break a story, not just a model. Consistent versus confirmed, the logic trap. Consistent with a comet. It sounds careful, and it is. But consistency is a hallway with many doors, and your brain picks the first one it sees. That's the primacy effect weaponized by bland language. Sparse data let multiple models walk through without bumping into each other. A dust-poor jet model can be consistent. A high area-to-mass, sail-like geometry can be consistent. A porous aggregate barely hanging together can be consistent. None of those statements reach the word everyone wants: confirmed. Here's the first trap. When evidence is thin, consistent with gets mistaken for supports. It doesn't. Consistency just means the model hasn't been eliminated by the data you have. That's useful, but it's not directional. Without likelihoods, the probability of the data given the model, you're comparing silhouettes, not bodies. The result is a linguistic drift. Internal notes say consistent with a comet. Headlines, hungry for nouns, become is a comet. There's a second asymmetry baked in. Extraordinary claims require extraordinary evidence is good hygiene, but it's often misapplied as ordinary claims require ordinary evidence, which can translate to almost no evidence at all. The active comet label feels ordinary. The burden slips. The alien sail hypothesis feels extraordinary. The burden balloons. In practice, both should face strong demands. One because it stretches priors, the other because it anchors policy and public memory. A wrong ordinary call misleads the next campaign as surely as an overzealous extraordinary one. Bayes gives a cleaner way to talk about this. Start with priors. Nature makes comets. We haven't confirmed any artifacts. So the prior odds favor natural by a wide margin. But priors aren't the finish line, they're the starting block. Likelihoods, how well each hypothesis predicts what we actually saw matter. A steady, sun-locked acceleration with no gas lines and no coma. A coherent high-amplitude light curve. An IR silence increase the likelihood of high area-to-mass geometry and decrease the likelihood of dust-poor, heat-poor jets. Posteriors live in that tension. Strong priors pulling one way, strong likelihoods tugging the other. Saying only consistent with a comet hides the tug-of-war. Language shortcuts warp memory. Public pieces quote consistent with in week 1 and comet in week 2. Month 3, people recall the simple noun. By the time you publish careful follow-ups, you're arguing against an impression, not a claim. That shift affects behavior. Proposal panels read active comet and prioritize gas diagnostics. If it's actually a sail-like body, the decisive measurements were polarimetry, specular flare searches, and rapid IR. Opportunities you already missed because the label steered the telescope. There's also a risk inversion. Calling it just a comet feels safe but can be bolder than it looks. It implies jets exist that no instrument found, heat exists that IR limits denied, and dust exists that stacks couldn't see. That's not caution, that's commitment by implication. Meanwhile, saying, we don't know sounds daring in public but is the most conservative scientific stance. The logic trap flips our instincts. You can see how this plays out in review. A manuscript arguing for radiation pressure gets asked to exhaust natural alternatives, and it should. A manuscript calling it an active comet should face symmetric scrutiny. Quantify the required gas production under dust and IR limits. propagate that through torque expectations, and show the orbit residuals prefer time-variable thrust. Too often, one side carries the calculations, the other leans on familiarity. Consistent with can be honest if you pair it with inconsistent with. For 3I Atlas, say both. Consistent with a comet model only if outgassing is dust-poor, heat-poor, and remarkably steady. Inconsistent with a normal active comet that matches Borisov-like behavior. Consistent with radiation pressure if the area-to-mass ratio is high and surfaces are broad. Inconsistent with compact, rock-like bodies. That framing keeps doors open while marking the ones that are effectively shut. The cleanest sentence we avoided was simple. Current data do not uniquely identify the cause of the acceleration. The highest likelihood fits favor a thin, broad geometry responsive to sunlight. Finely tuned, dust-poor outgassing remains possible but strained by spectral and thermal limits. Say that up front and you trigger curiosity, not certainty. People lean in when you give them a mystery with rules. That isn't clicky, it is true. And the next observation strategy should have flowed from that statement, not from a noun that got there by drift. The quiet schism, what researchers actually debated. While the public line hugged Comet, the private channels split into two working camps that on paper agreed about almost everything except which discomfort to accept. Camp A argued for an exotic but natural body and guarded methodological conservatism. Their mantra: start with priors, punish overfitting, and don't let first-order anomalies drag you into second-order speculation. Camp B said, keep the artificial geometry hypothesis on the table because it makes specific, testable predictions the data already seem to favor. Their refrain: if sunlight can explain the push and the light curve, test sunlight's fingerprints, not vents we can't find. The debates weren't about aliens versus science. They were about procedure. Camp A focused on bounding what dust-poor outgassing could still do within the limits. Could micro-vents create a near-constant A1 term if thermal inertia and vent latitude line up? Could large, nearly invisible grains escape detection yet carry momentum? Could catalog systematics or station weighting inflate a non-grav signal? They wrote checklists, combed residuals, and asked review board questions before a paper even existed. Camp B kept returning to predictions. If the geometry is thin and broad, then polarimetry should show polarization angles and degrees consistent with smooth, coherent surfaces, rather than fluffy coma grains. The light curve should exhibit occasional specular flares at predicted solar phase angles. The non-grav term should remain dominantly radial with minimal time variability. Thermal IR should stay quiet within a calculable envelope for a radiator that bleeds heat on both sides. Each was falsifiable. None required a press release about intention. Then telescope time got political, as it always does. Proposals framed around active comet characterization sounded familiar and low risk. Proposals framed around thin film surface diagnostics sounded niche and to some panels premature. A few nights went to each, but cadence matters. Camp A landed more astrometry and broadband photometry to stabilize the orbit and refine the light curve. Camp B tried to wedge in polarimetry and rapid response IR during key phase angles, only to watch whether erase windows or scheduling push them past geometry sweet spots. In one private exchange, a senior investigator drafted a neutral abstract: Interstellar Object exhibiting sustained non-gravitational acceleration and high-amplitude coherent light curve. We evaluate outgassing and radiation pressure scenarios. Outreach flagged it as murky. Another version became Interstellar Comet with evidence for weak activity. The change wasn't science, it was optics. Camp B bristled. Camp A shrugged, arguing that language shouldn't outrun peer-reviewed analysis either way. Meanwhile, whiteboards filled with "what would convince you?" questions. Camp A's list: a secure detection of any gas line consistent with the required thrust, time-variable non-grav terms matching thermal lag models, measurable torque evolution linked to putative vents, coma detection at lower levels with deeper stacks. Camp B's list: polarimetric signatures incompatible with coma grains, reproducible specular glints at predicted geometries, phase curve behavior that matches flat facet scattering models, continued IR silence across a range of heliocentric distances consistent with a thin radiator. There was a third, quieter axis: careers. Junior researchers felt the geometry of risk: write radiation pressure in a title, and your name could get stapled to an internet narrative you never endorsed. Stick to activity constraints, and your CV reads clean, your reviewer pool friendlier. Mentors had opinions colored by scars from Oumuamua. Some advised playing inside the lines until the signal forced a bolder claim. Others said the only way to get decisive data is to argue for the measurements that can decide it, even if the word "sail" makes comms teams twitch. Data-driven compromises emerged. A joint plan proposed high-cadence photometry to capture microstructure in the light curve that jets should smear but facets might sharpen, polarization sequences at two-phase angles to separate grain clouds from films, and a coordinated effort to capture any sudden color shifts that would betray episodic venting. It wasn't flashy, but it was a blueprint. Winning time for all three proved harder than writing the plan. Another friction point was priors versus likelihoods. Camp A leaned on population. Nature sprays out comets. Artifacts have no confirmed precedent. Camp B leaned on fit quality. The combination of sun-locked acceleration, IR quiet, spectral silence, and coherent high amplitude made radiation pressure a higher likelihood explanation than dust-poor jets. Both were right in their domains. The schism was about which axis should dominate decision-making when the clock was against them. Even the choice of error bars became a front. Conservative inflation of uncertainties in astrometry softened the non-grav requirement, buying Camp a space. Narrowing photometric systematics sharpened the light curve features, feeding Camp B's case for facets. Everyone was trying to be honest. Everyone knew how small technical choices nudge narratives. Slack threads read like micro-trials. This waiting, that cut, these nights excluded. Does the A1 term persist? Does the period stay coherent? And under it all, a shared frustration. This was solvable with the right data and time. Polarimetry, early IR, coordinated specular flare hunts, none was exotic. All were doable if the label hadn't pre-sorted priorities and if weather had played nice. The quiet schism never became a public feud because the people in it still wanted the same thing: a clean kill shot on the wrong model. They just disagreed about which model was most likely wrong and which measurement would prove it fastest. If artificial, sail scenarios and motives. If you let yourself step into the artificial lane for a minute, the pieces don't require magic. They require engineering that knows the sun. Start with the simplest archetype: a passive solar sail, no propulsion other than photons, no onboard fuel. Think a thin, broad sheet, meters to hundreds of meters across, kept thin enough that its aerial density sits in the grams per square meter range. That already lands near the acceleration scale we back solved. Give it modest reflectivity and a bit of stiffness, and sunlight does the rest. Now give that passivity a little attitude control. Not full steering, just trim tabs, slight tilts, mass offsets, or reflective patches arranged to create self-stabilizing torques. Under constant sunlight, a sail like that can weather vane into a steady attitude, explaining the coherent light curve and the calm non-gravitational term without frantic corrections. No thrusters needed. If you want occasional glints, polish a few zones. As the sail tumbles or processes slowly, those specular patches send brief flashes that ride on top of the broader brightness swings. Observers hunting for flare timing could test this, but our cadence missed most of those chances. Materials matter, and here, where artificial doesn't need to be exotic. Human labs already play with polyimides, aluminized films, and ultra-thin composites in the tens of microns class. Over interstellar timescales, micrometeoroids will pockmark those surfaces, reducing specularity and slightly raising emissivity. That weathering pushes the spectrum toward neutral to slightly red and keeps infrared output subdued because a large radiator bleeds heat on both sides. The very aging that dims the mirror look also helps hide thermal signatures. You don't need a perfect mirror to ride photons. You just need low mass and enough coherence to keep the sheet from crumpling. What would an interstellar sail be doing here? One plausible answer is nothing directed at us. Think drift probes, devices seated long ago on slow, energy-minimal trajectories, using only stellar radiation to coast between systems. You don't aim them like arrows. You release them into galactic traffic and accept long travel times. Their job might be to sample dust environments, map magnetic fields, or act as passive beacons for anyone who knows how to look. A mothership releasing smaller probes reads dramatic, but a more grounded picture is a carrier that sheds wafer-scale scouts at perihelia to harvest power or perform close pass measurements, then leaves them to die while the parent sheet continues on. Kinematics become clues. If a sail arrived with a velocity near the local standard of rest, that points to drift deployment. It wasn't gunning for our sun. It was passing through the neighborhood we happen to share with many stars. If the entry vector aligns with no obvious origin but avoids deep dives into the inner system, that favors endurance over reconnaissance. A targeted probe would likely take risks to lower perihelion for power and data. A drift sail keeps margins. Our fits showed a clean hyperbola, a safe miss distance, and no last-minute steering signatures in the residuals. That aesthetic leans passive. Survivability is the hard part, and it sets design rules. Over millions of years, micrometeoroid hits eat area and threaten catastrophic tears. Engineers fight that with redundancy, mesh-reinforced films, ripstop patterns that localize damage, and thickness gradients that strengthen key load paths while keeping most of the sheet ultra-thin. Radiation embrittlement can be slowed with coatings. UV darkening changes albedo but not necessarily structure. A sail doesn't need to stay pristine. It needs to stay broad. Even a battered, perforated sheet presents area to photons. Communication expectations trip people up. If it's artificial, why no signal? Because transmitting across interstellar distances takes power and antennas that a wafer-thin sail won't carry unless it's the whole point. For a drift platform, silence is the default. Data could be stored for centuries, and only uplinked when a rare alignment brings the sail close to a star with harvested energy or near a relay node. From our vantage, that looks like radio silence forever. Meanwhile, optical glints or polarization signatures become the only accidental broadcasts. We didn't catch compelling radio. That doesn't falsify an unpowered design. What about maneuvering? A smart sail could, in theory, pivot to adjust its trajectory measurably. Our residuals didn't demand such steering, and that's telling. A low-power philosophy prefers geometry that self-stabilizes and soaks up torque from sunlight without constant corrections. If anything, the slight stability we inferred, coherent period, steady acceleration, resembles a sail trimmed to a comfortable attitude and left alone. If intention hides anywhere, it hides in how uneventful the dynamics were. There's a darker motive people raise, surveillance. But surveillance of what at kilometers per second with no braking? A pass like this is a blur. A more plausible motive is census. Drop sails across the galaxy, let them drift through systems and measure the same baseline physics, dust, fields, radiation in many environments. If you seed enough, a few will wander into telescope beams. You don't need to know we're here. You just need to cover the map. Even the phase curve oddities fit an engineered surface that's been aged. A thin film over micro-rough substrate produces opposition surges of the kind we saw, without the fluffy scattering signature of coma grains. Add patchy reflectors, either by design or by scar, and you get asymmetric brightness peaks at certain geometries. Those become testable. If future objects show repeatable flare-phase relations, you build a catalog and see if a class emerges. Ethical leap, calling it intentional, stays beyond the data. The physical leap, accepting a high area-to-mass, thin, broad geometry that sunlight can push, is what the numbers already allow. Artificial scenarios simply choose engineered materials over exotic ices to reach the same dynamical behavior with fewer thermal and spectral contortions. The motive, if any, remains a story we can't read from photons alone. But the sail, quiet, self-stabilizing, durable enough to drift, needs no manifesto. It only needs a star. If natural, the exotic debris hypotheses. If you keep the origin natural, you're not choosing normal, you're choosing a wilder branch of nature. Start with the N2 iceberg idea, reborn from the Oumuamua debates. Nitrogen ice is bright, reflective, and volatile enough to sublimate far from the sun, which could, in theory, supply gentle thrust with minimal dust. But 3I Atlas didn't show the telltale nitrogen sublimation lines, and the infrared limits didn't play nice with a skin warm enough to sustain steady mass loss. There's also a supply problem. Producing planet-sized volumes of N2 shards via Pluto-like crust stripping needs a population we don't see and a collisional history that keeps spraying for eons. Rare isn't impossible, but rare enough has to close the numbers, and here it doesn't. Slide to hydrogen snowflakes, ultralight H2 aggregates formed in dark molecular clouds and lofted out of nascent systems. They promise enormous area for little mass, ticking the radiation pressure box without invoking engineering. The trouble is survivability. H2 is famously skittish. Even cosmic ray heating and UV over millions of years chew through it. You can bury it, then it can't drive surface processes. You can keep it exposed, then it evaporates long before arrival. Lab analogs suggest fragile aggregates compact or sinter under cycling, collapsing precisely when you need them broad and airy near perihelion. CO and CO2 frosts in multi-layer mantles offer another route. Imagine an interstellar shard with stratified volatiles under a refractory crust. Sunlight warms the crust, volatiles percolate through micropores, and ventless thrust emerges as gas seeps uniformly. No jets, no dust, just a faint push. Clever, but the thermodynamics bite back. Permeability evolves. Channels open and clog. Thrust should wander with diurnal cycles and rotation. The orbit's acceleration looked steady across weeks, and the spectrum didn't reveal the faint emission bands you'd expect even from poor flow. If the flow is too weak to see, it's likely too weak to move a hyperbolic visitor measurably. Then there's the fractal raft idea. Tidal shredding near a giant planet or star tears a differentiated body into thin, pancake-like plates, silicate or carbon-rich sheets glued by Van der Waals forces. These rafts could present large area with minimal thickness, coupling to sunlight without being engineered. It's an elegant picture, but production is the choke point. You need disruption events frequent enough across the galaxy, plus a fragmentation pathway that preferentially leaves broad, coherent sheets instead of ribbons or dust. After that, those sheets must survive interstellar sandblasting without curling, crumpling, or being perforated into lace. A few might endure, billions likely won't. People try population math to rescue these scenarios. Start with every planetary system, multiply by disruption rates, propagate ejection probabilities, fold in detection biases, and ask how many candidates we should see in a decade of surveys. The answer wobbles wildly with assumptions. Still, to get a third interstellar visitor looking this non-cometary, you either accept that surveys preferentially snare ultra-thin oddballs, or you accept that nature makes thin rafts at astonishing rates. Selection effects help. Thin, bright objects are easier to spot at the margins, but selection can't invent dynamics like a sun-locked acceleration. It can only bias what we notice. Another natural path sketches foamy silicate aerogels, porous aggregates born in high-velocity impacts, then fluffed by electrostatic forces in protoplanetary disks. Their low density raises area to mass, and their emissivity keeps them cool. Yet the same porosity that boosts radiation pressure also makes them vulnerable. Micro-impacts erode foams efficiently. Thermal cycling compacts pores. Radiation stitches bonds. Over interstellar timescales, you drift toward denser, duller lumps. The light curve's crisp amplitude and the rotation stability we saw don't love a sponge changing shape under heat. Ventless thrust via thermal desorption got a short hearing. Solar photons liberate adsorbed molecules from a surface, yielding a slow, continuous recoil. The physics is real, the thrust is minuscule, and it plummets as adsorbates deplete. To sustain week-long measurable acceleration, you need reservoirs that refill or an initial load thick enough to glow in IR, which it didn't. Electrostatic lofting came back too. Charge the surface, hop grains off the day side, get a recoil without a coma. Except lofting wants local fields, and the grain trajectories should add flicker and color shifts we didn't see. Could we be staring at a dormant comet that fluked a smooth A1 term? Dormant means crusted over, vents sealed, no coma, so where does the push come from? Sublimation under a crust should eventually blow out, leaving dust scars or transient brightenings. Instead, the brightness modulation stayed clock-like and stacks stayed clean. Dormant doesn't pair well with steady recoil. What about composition camouflaging its activity? A carbon-rich, low-albedo skin could absorb sunlight, keeping the surface warm enough for light desorption but dark enough to hide lines. That skin would still radiate in IR unless it's thin and efficiently cooled. Ironically, back to a plate-like geometry. Every detour toward hidden activity loops back to shapes that behave like sails, whether or not intention sits behind them. The hardest constraint is the combo platter. Sun-locked acceleration, IR quiet spectral silence, coherent high-amplitude light curve. Natural hypotheses can hit 1 or 2 cleanly, occasionally 3 with tuning. Hitting all 4 without visible side effects stacks contingencies. You can argue rarity, this could be the oddest shard we've met. But then population has to carry the weight. If objects this tuned are vanishingly rare, catching one so early in our interstellar census is an odd coincidence. If they're common enough to see now, their formation needs a robust, galaxy-wide factory we haven't identified. None of this says nature can't surprise us. It has, repeatedly. It does say the burden shifts from prove aliens to show me a natural pipeline that prints thin, broad, durable rafts at scale and leaves them quiet in spectra and IR. Until a lab analog survives a punishing bake, blast, and spin gauntlet, or a model closes both production and survival numbers, the exotic debris lane stays open, but narrow. And every step we take down, it looks more like we're describing a sail without admitting the word. The testable future, what could settle it next time? The next interstellar visitor won't wait for our debates. If we want answers, we need a playbook ready before the alert hits. It starts with triggers. When a survey flags hyperbolic motion, an automated pipeline should fire off immediate spectroscopy requests across longitudes, optical and near IR within hours, not days. The first 48 hours decide what we can rule in or out. Even low SN spectra can catch fleeting emission bands if venting spikes early. Miss that window and you chase ghosts. In parallel, we need dedicated wide-field infrared eyes. A small, always-on IR facility tuned for rapid response could lock down thermal signatures before the object fades. Not a flagship observatory, just a nimble instrument that trades aperture for speed. If activity is real, the skin warms. If sunlight is the engine, a thin radiator stays cool. Early thermal curves cut through a dozen speculative models. Pair that with mid-IR if geometry allows, and you can bracket thermal inertia and surface emissivity in a single night. Polarimetry has to move from nice to have to go now. Linear polarization as a function of phase angle can tell you whether you're looking at coma grains, rough regolith, or smoother thin films. The polarization phase curve of a flat facet doesn't look like a fluffy coma. Build an alert network that auto-allocates polarimetric sequences to small and mid-sized telescopes with standard filters and shared calibration stars. 2 well-timed angles can do more than a week of broadband guesses. Spin and specular checks come next. High-cadence photometry with coordinated ring, coverage, multiple sites staggered in longitude, can capture microstructure in the light curve that jets smear and facets preserve. Add a glint hunt, predicted phase angles where specular flashes should occur if smooth patches exist. A 5-minute cadence across an hour at those angles can confirm or kill the paneling hypothesis fast. Publish the predicted windows openly, so amateurs with fast rigs can pile on and expand coverage. Astrometry still matters, but we need to harden it. Commit to a homogenized reduction pipeline from the start, same catalogs, same plate solving, transparent weighting, and nightly cross-checks among stations. Build a rapid reprocessing loop that updates the orbit fit each night and flags when a non-grav term emerges above a threshold. When it does, branch the strategy. One path chases gas diagnostics, the other locks in radiation pressure tests. Radar is the long shot, but when range and geometry align, it's a kingmaker. Coordinated planetary radar attempts could constrain size and, if you're lucky, aspect, though interstellar targets are usually too far and fast. Even a non-detection at a defined SNR ceiling can bound cross-section, feeding back into albedo and thickness estimates. Treat radar like a lottery ticket you buy whenever odds aren't terrible. We also need to mine the past better. Archival reprocessing with motion-aware algorithms can pull out faint comets or tails missed in real time, especially if activity flickered before discovery. Train difference imaging pipelines on synthetic injections of thin-facet light curves so they don't scrub out the very signals we need. And commit to immediate public data release with standardized metadata. Filters, exposure times, tracking rates, seeing. Open data turns curiosity into capacity. Speed requires structure. Create an interstellar rapid response consortium with pre-cleared observing blocks on partner telescopes. No ad hoc emails, no last-minute scrambles. A living checklist, spectra within 12 hours, IR within 24, polarimetry at the first 2 usable phase angles, cadence photometry nightly for a week, automated orbit updates posted daily with residual plots anyone can audit. Publish a rolling "What would change our minds" list so the community knows which measurements move the needle. Communications need a parallel upgrade. Commit to neutral, precise public language from the start. Interstellar Object exhibiting X, testing for Y and Z over the next N days. No labels, just hypotheses and timelines. Pair each update with the measurement rationale. Why polarimetry matters, what a non-detection in IR implies, how a radial A1 term differs from thermal lag. If you educate as you observe, you buy patience and keep the narrative honest while the data land. Finally, practice. Run tabletop exercises with simulated alerts, fake an interstellar target in the stream, trigger the network, time the handoffs, measure the lag. Fix bottlenecks now. The fourth interstellar visitor is inevitable. If we meet it with a rehearsed, open, and test-driven plan, the argument shrinks and the evidence grows. And maybe, for once, the label follows the data instead of leading it. Media, memes, and memory. How narratives fossilize. First impressions harden. Consistent with a comet becomes is a comet, then a meme, just a comet. Corrections lag, nuance underperforms. Creators chase clicks, institutions chase safety. The result? Future proposals, headlines, and even classroom slides inherit that frame. This is anchoring plus availability bias. The first noun sticks and the loudest clip repeats. Communicate uncertainty clearly, early, and often, or the next object's truth arrives pre-decided. Back to the room, the choice in real time. Back to that control room. 2 drafts sit on a laptop. Active comet and object with non-gravitational acceleration. Same data, different futures. The senior scientist leans on the table, thumbs hovering, knowing one noun will steer telescope time, headlines, and what their students decide to work on for the next 6 months. The room is quiet except for cooling fans and the soft tick of a tracking mount. Everyone knows what happened last time we hesitated. A junior postdoc clears her throat. Can we change just one word? Consistent with 2 exhibits. It's true either way. Heads nod, then shake. Someone worries aloud about reporters lifting the phrase non-gravitational without the context and turning it into a circus. Another points at the orbit plots. The radial A1 term, stable and boring, is either sunlight or an invisible jet that never blinks. If we say comet, we're implying a jet that none of our instruments found. Micro story. At 1:17 a.m., an email goes out to the press liaison. Request: swap active comet for interstellar object exhibiting a steady sun-locked acceleration. Activity unconfirmed. The reply lands at 1:29 a.m. Appreciate the nuance. We're locked for the morning brief. Too risky to change framing now. The draft sticks. The scientist closes the window and stares at the glow of the other screen, residuals hugging the model only when the extra push is turned on. A grad student scrolls the light curve. The amplitude S not going anywhere, he says, half to himself. If jets were doing this, we'd see period drift. Another voice from the back. We need polarimetry. If we had it tonight, we could settle the surface question. But the night is already sliced. Half to astrometry to keep the orbit pinned. Half to broadband photometry feeding a curve that already looks like a panel. Polarimetry didn't make the cut because the abstract said comet. And comet abstracts don't usually ask for polarization first. There's a human geometry to curiosity. The junior folks measure their words. One already caught flack for mentioning Oumuamua in a Q&A and doesn't want to be clipped into a montage about aliens. Another is on the job market and can't afford a referee's eye rolling at sale. So they couch it. We should avoid overcommitting to a volatile-driven model without corroborating lines. It's courage in passive voice. The missing sentence hangs over the keyboards. We don't know yet. That line, spoken plainly, would invite the right questions. It would justify polarimetry over another safe night of photometry, IR over another comforting press hit, a glint hunt over routine cadence. It would make the uncertainty a shared project with the public instead of a private worry behind closed blinds. But the muscle memory wins. The label that comms calls gets the space. One of the instrument leads pulls up scheduling. There's a phase angle window for speculars in 36 hours. If we post a public call, amateurs could stack it. Outreach shakes their head. Not if the brief says comet. They won't chase glints for a comet. The irony lands hard. A single word closes a door the data could have opened. The draft goes out. Interstellar Comet Candidate 3I Atlas, consistent with cometary behavior, shows a small non-gravitational acceleration. Accurate, safe, incomplete. The relief in the room is mixed with a quiet regret. The senior scientist turns to the team. We write the methods exactly as we see them. The preprint says what the data say. Nods all around. Then softer. Next time we fight for the right sentence up front. Hours later, the coverage appears. Headlines compress. The noun hardens. Telescope committees skim. Proposals with activity in the title get quick approvals. The polarimetry request is marked intriguing but speculative. Resubmit with stronger justification. The team keeps working. More astrometry, more photometry, better fits, but they can feel the current. It's not malice, it's momentum. In a quieter corner, the postdoc drafts a note for the group's public page. It's short. 3I Atlas exhibits a steady, sun-aligned acceleration without a detected coma or gas lines. Its light curve shows high-amplitude, coherent modulation. We're testing out gassing and radiation pressure scenarios with new observations. It's the sentence they wanted to lead with, posted where fewer people will read it, exactly right and a little late. They hit publish anyway. Small language choices ripple. Sometimes they make their own weather. Resolution and broader meaning. Truth here isn't a noun. It's a verb that only works when we let evidence outrun our comfort. If this hooked you, it's because your curiosity gap is still open. Close it with better data, not safer words. If you want the next interstellar visitor met with open hypotheses and decisive tests, stay with us. Subscribe, share this, and watch our Oumuamua deep dive next. Then tell agencies you expect, we don't know yet, said loudly and early.